Hello everyone, and welcome to our NeurIPS 2025 presentation. Today, we are excited to introduce our paper titled Backpropagation-Free Test Time Adaptation via Probabilistic Gaussian Alignment, referred to as ADAPT. Vision language models like CLIP are powerful, but their robustness drops significantly under distribution shifts. TTA offers a promising solution to enhance the robustness of VLMs by adapting them using only unlabeled test data. Early approaches, including prompt tuning and adapter tuning methods, rely on backpropagation. This leads to high computational cost, making them impractical for real-time scenarios. Even some similarity score-based TTA are training-free, but lack explicit class distribution modeling. On the other hand, transductive learning, especially GDA-based transductive TTA, has also gained attention, which can model class-conditional feature distributions and assign labels based on likelihood estimation. However, such methods often require complete access to target data, or even source data, making them unsuitable for strict online or streaming environments where samples arrive and are processed sequentially, one by one, without access to future data. This brings us to our core research question: can we design a backpropagation-free and distribution-aware TTA framework that seamlessly supports both online and transductive adaptation? Our approach is built on two key empirical observations. First, class-conditional CLIP features are approximately Gaussian. To verify this, we adopted a projection-based testing strategy, applying normality tests like the Henn-Circler and Shapiro-Wilk tests. As you can see in the table, the average p-values frequently exceed the 0.05 threshold, which provides strong statistical support for our Gaussian assumption. Our second observation is that these Gaussian distributions appear to share a common covariance matrix. We measured this in two ways. The histogram on the left shows that the Frobenius distance between class-specific and pooled covariance is extremely small for almost all classes. Meanwhile, the heat map on the right reveals a strong, consistent structural pattern, providing further evidence for a shared covariance structure. Motivated by these two findings, we form our core assumption that class-conditional CLIP features follow a Gaussian distribution with a shared covariance matrix, as defined by this equation. Under our core assumption, in this work, we introduced ADAPT, an advanced distribution-aware method for backpropagation-free test time adaptation. As shown in the overview figure, our ADAPT performs TTA by modeling class-conditional feature distributions under a Gaussian assumption with shared covariance across classes. Class means are initialized from CLIP prototypes and refined using high-confidence samples in fixed-size per-class knowledge banks. Predictions are made via a closed-form, backpropagation-free solution. Specifically, in the online setting, a standard GDA classifier suffers from severe likelihood bias due to limited samples and overconfident early predictions. To solve this, we introduce a regularized objective that corrects this bias using both the CLIP prior and our knowledge bank. By minimizing this objective, we successfully derive a new closed-form solution for efficient updates. Our framework elegantly extends to the transductive setting. Since the entire test set is available, we simply extend our regularized objective over all samples. Crucially, this admits an identical closed-form solution, allowing our transductive method to also run in a single, optimization-free pass, unifying both TTA settings. We summarize the procedure for online ADAPT in Algorithm 1 and transductive ADAPT in Algorithm 2. Notably, both procedures are fully training-free and sub-iteration-free. We evaluated ADAPT on 3 different tasks. Let's begin with Task 1, Natural Distribution Shift. As the table shows, in the online setting, ADAPT achieves the highest average accuracy at 66.53%, outperforming all baselines. Notably, this performance is so strong that it even surpasses several powerful transductive methods. In the transductive setting, ADAPT further improves to 67.09%, ranking first on these OOD benchmarks. Task 2, Corruption Robustness. On 15 synthetic corruptions, ADAPT again achieves the best performance in both the online setting at 28.56% and the transductive setting at 30.29%. This demonstrates strong robustness even under severe visual degradations. Task 3, Fine-grained categorization. Here, ADAPT achieves significant gains over the CLIP baseline, over 7% online and nearly 9% transductive. Remarkably, our method narrows the gap to the Oracle performance, which uses ground truth labels, to within 5%. We also conducted ablation studies. The table on the left shows that removing the knowledge bank, B, causes a significant performance drop, confirming its critical role in mitigating bias. We can see that online performance is unstable when L is small due to limited statistics, but stabilizes once L than or equal to 8. In contrast, the transductive setting is robust to L as all target data are available. We use L equals 16 for online and L equals 6 for transductive. For the hyperparameter alpha, performance steadily improves with larger alpha, confirming that ADAPT benefits from reliable historical samples over static clip priors. We set alpha equals 0.9 to balance prior knowledge and adaptivity. To further analyze the efficiency, we evaluate all methods under the same protocol and computational resource, NVIDIA RTX A6000. In the online setting, ADAPT achieves the highest accuracy with just 1 hour 11 minutes and 0.93 gigabytes, notably lower than TPT. In the transductive setting, it builds the knowledge bank once and runs in a single pass, requiring only 0.73 minutes and 3.37 gigabytes. These results highlight ADAPT as a practical solution balancing accuracy and efficiency. Our method is not limited to CLIP. We also evaluated ADAPT on other VLMs, including BLIP and ALBEF. As these bar charts show, ADAPT consistently improves performance over the baseline across all tasks and model architectures, demonstrating its general applicability. We also visualized the decision boundaries. As you can see, methods like CLIP and TPT have irregular and unstable boundaries. In contrast, our ADAPT, both online and transductive, builds smooth, compact Gaussian-based boundaries, achieving better class separation. In conclusion, ADAPT is a novel, backpropagation-free TTA framework that unifies online and transductive adaptation by modeling shared covariance Gaussians. Please check our project page for code and more details. Thank you for your attention.